Welcome to a lesson with Dr. Powell. Let's look at an example of finding the components of one vector along another one using complex multiplication. Let's suppose that we have a complex number, v is equal to 1 plus 2i. Suppose that we have another one, roughly somewhere over here. W is equal to negative 4 plus 3i, say. All right. Now, we'd like to put, let's suppose we want to do V and project it onto a ground W. So that would be like, so we have a distance L1 to compute, a distance L2 to compute right here. Okay, so these can be done via complex multiplication. All we need to do is take this guy, 1 plus 2i, and we multiply it by the complex conjugate of that guy, negative 4 minus 3i. Now think about what this means. You take the complex conjugate, you're going to get something over here. So something in this direction means that we've actually done a rotation, and this rotation is actually from this old positive x-axis. So, or to it rather. So kind of what we want to do is we want to change our picture. See this? So we want to be able to rotate this guy, this W bar. Let's see. So yeah, so we want to rotate this. Okay, so in this rotation, what we're doing is we're making W bar where what we're measuring everything from. So this is the new x-axis, and let's think about okay how W corresponds in there. So we're the angle over to W from the old x-axis is like way like this. So similarly, actually, the angle that if this is the positive x direction that we're using when we're plotting W with that angle, we're actually plotting this angle from it in a counterclockwise direction over to here. So actually this guy in this multiplication will actually wound up over here facing in this direction, meaning that when we actually do this casting, the real part will actually be positive, and we'll see that because the ground is actually moved over there to the positive direction. Let's see that in action. So remember how we get the L1. It's just the real part of this multiplication, and then we have to divide by something. We divide by the length of what we're expanding by, which is W itself, which is the length of W itself, or which is or the length of W bar. They're the same. So you can do that via the Pythagorean theorem, 4 squared plus 3 squared, square rooted, and that would be 5. You could just think of a 3, 4, 5 triangle. So the real part divided by 5 is actually what L1 is equal to. And notice when we compute this, we have 1 times negative 4. So negative 4, and then we have 2i times negative 3i. So it's like a negative and then an I squared. So that's another negative. So 2 negatives make a positive. So it's really just 2 times 3. So plus 6 divided by 5, which is equal to 2/5. Notice what we did here. The I squared provides a negative, and the conjugate supplies a negative, but the two negatives cancel each other out. So we may as well have just written this as 1, 2 without having done the conjugate or using an I squared at all. Just thought strictly 1, 2, negative 4 comma 3, and just simply multiplied these guys through. 1 times negative 4, so first and last, plus 2 times 3. So 1 times negative 4 plus 2 times 3. So quite literally first plus last, where you don't do any imaginary and you also don't do any conjugate. So, and this only works for the real part though, by the way, but you could do this. This process is called a dot product between two vectors, where we just take corresponding components, like the x components and the y components individually, multiply the corresponding components, then add up the results. Like the two x's multiplied together, the two y's multiplied together, then add the results. That's called a dot product. So really L1 quite literally can be thought of as the dot product of, so we get u So we can just write this formula as u dot v, but divided by, or actually not u, I guess this is, sorry, this is v, the vector v. Let's just get that right. So the vector v dot the vector w, right? Just as vectors, and you can even use vector notation for the dot product. Divided. Now notice what the dot product is. The dot product is actually a number, which we can call a scalar for vectors. So v dot w is a number. And the length is also a number of w, okay? So this is like v dot w. And this outputs, so this is kind of an interesting product because you take two things and multiply them together and you don't get a vector, you get a number. So this dot product gives you a number, but and that has to do with because it's giving you a real part. It's giving a real part of a complex multiplication, which is just a number itself. So, and it's not even, so it's real all of a sudden and not complex. So it should make sense there. And then this is just a length as well. Another way of thinking about it is you could just do v dot w divided by w bar. Now this is interesting because this vector right here, you take a vector and you divide it by its length. This all of a sudden has a length of 1. So so it's like v dotted with a unit vector length. And that actually equals that projection. So in general, you can use complex multiplication, but see how it winds down to a formula here where you actually can go v dot some unit vector in the direction of w. So in the direction of w, if I take a unit length in that direction, which you can simply get just by taking w itself and dividing by its length, getting something and then dotting it over with v. I prefer to actually make this computation, v dot w, and then in the end dividing by that length. That works more cleanly anyhow. But in general, if you dot something with a unit vector, it actually gives you a projection. Projection always happens if you dot with unit vector. So v dotted with a unit ground is the projection length. V dotted with a unit ground, so unit ground is the projection length. All right. Well, anyhow, we get 2/5. Great. Okay, let's take a look at the next one. L2. How do we compute L2? So I really like the complex multiplication for the L2 part. The L2 part is the OI, right? And you're also dividing by 5 here. So the OI part of this. But you have to look at the complex multiplication, not this one when you do this. And you do have the conjugate in there. That's important in this. And you need the full strength of it in order to get the L2. So it's the OI, which is just simply this guy and that guy added together, right? So 1 times -3, which is -3, and then you have 2 times -4, which is -8. So we end up getting -11/5 is L2. Now, does that make sense as we're looking at this? Okay, so L2, well, think about how this is rotated here. So if this is now lined up with the positive x-axis, this guy has actually turned down around, and this vector, so think about this vector w is now kind of on the x-axis going in this direction. This guy is now like this. It makes perfect sense that this L2 will be a negative number, -11/5, and it makes sense as well that this L1 will be positive. In fact, L1 is always positive when this vector actually projects onto this vector. In this sense, if this angle right here is acute, okay, if this is an acute angle, then it'll definitely be positive down there. When would it be negative? Well, if we were out here and then when we rotate, see how this is obtuse. So if that was obtuse, then this angle being obtuse would be out here, and then L1 would be negative over there. So it's just a matter of being acute versus obtuse. you end up getting the projection, or you end up getting these L1 positive or negative. L2 in this case, just because of its positioning, the vector V is counter. So V is actually clockwise away from, notice how V is clockwise away from W, so that when you rotate it, it's like going downward. That's why it was negative. So if you can, so from the ground, you take the ground and you draw an arrow to, the vector, kind of this, at least this in the smaller angle, suppose, and like this. If that angle is clockwise, and this is an acute angle, you're going to be down negative down there. And if it's, but if the ground was on the other side, then we would actually be, then it would actually be positive. So the imaginary part kind of flips up and down, and that's kind of a visualization of what's going on with that. But nonetheless, you take the absolute value of this and you would get L2. So I've put a lot of commentary into this, but the short of the matter, it's not too challenging just to use this multiplication quickly to get what the real part is and what the imaginary part is, which is just this perpendicular component, or sometimes called orthogonal component, and this component along the ground right here of the projection of V onto W. Thanks for watching.